I've been asked more than once across these conversations about specific pieces of the Mars mission puzzle, the orbital mechanics, the propellant problem, the radiation exposure. I want to use this conversation to step back and answer a more fundamental question. What is the actual underlying reason a Mars return mission is so much harder than simply getting there in the first place? I don't think the answer is any single obstacle. I think it's something more structural. And once you see it clearly, I think it explains why so many individually solvable engineering problems combine into something genuinely formidable. The real reason I've come to believe is this. A Mars return mission is the first spaceflight endeavor in human history where the return journey depends on infrastructure that has to be built, tested, and proven reliable on another planet years before any human being ever needs to rely on it, with absolutely no possibility of sending help, spare parts, or a rescue crew if that infrastructure fails. I want to unpack that statement carefully, because I think every specific technical difficulty people usually point to when discussing Mars return missions is actually a symptom of this one underlying structural problem, rather than an independent difficulty in its own right. Consider how every previous human spaceflight program has handled the return journey when Apollo astronauts left Earth for the moon, their return vehicle, and all the fuel it needed, launched with them from Earth, fully fueled, tested and verified before departure, using infrastructure and expertise available in unlimited quantity back home. When astronauts board the International Space Station, their return capsule remains docked and available throughout their stay, continuously monitored, with backup vehicles and emergency return options available on a timescale of hours if something goes seriously wrong. Every human spaceflight program before a Mars mission has kept the return capability either fully prepared before departure or continuously accessible and serviceable throughout the mission. A Mars return mission cannot work this way for a reason rooted directly in the physics I've discussed in earlier conversations. The fuel required for the return journey is too massive to carry from Earth alongside everything else the mission needs. I want to walk through why this specific constraint is the seed from which nearly every other difficulty in a Mars return mission grows. The rocket equation, which I've discussed before, in the context of interstellar travel, applies here with full force even though the velocities involved are vastly smaller than anything approaching light speed. Every kilogram of return propellant carried from Earth has to be accelerated across the entire outbound journey to Mars, which means it requires its own additional propellant during the outbound leg to accelerate that mass, which itself adds further mass in the same compounding exponential relationship that makes high-velocity propulsion so demanding in any context. For a mission architecture large enough to support a human crew safely on the surface for the extended stay, orbital mechanics requires carrying sufficient return propellant from Earth, multiplies the total mission mass to a degree that every serious mission architecture study, going back decades, has concluded is not practically achievable within any realistic budget or launch capability. This single physical constraint is what forces mission planners toward in situ resource utilization, manufacturing the return propellant on Mars itself, using local resources rather than carrying it from Earth. And this is where the real structural difficulty of a Mars return mission actually originates, because it means the entire success of the return journey depends on equipment that has to be transported to Mars, landed successfully, and then operated continuously and reliably for an extended period, manufacturing thousands of kilograms of rocket-grade propellant, entirely autonomously, with no human being present to troubleshoot problems well before any crew ever launches from Earth to begin their own journey. I want to be specific about why this timing requirement is so unforgiving. Mission architectures that rely on Mars-based propellant production generally require the production equipment to arrive and begin operating a year or more before the crew even departs Earth. Specifically so, mission planners can confirm the propellant production is proceeding successfully before committing a crew to a mission that depends entirely on that propellant being ready and waiting when they arrive. This means the single most important piece of technology for the entire mission's safe return has to work correctly, autonomously on an alien planet for a year or more, without any possibility of a technician traveling out to fix it if something breaks, and without any possibility of the crew departing Earth until this remote, autonomous manufacturing process has already proven itself successful from tens of millions of miles away. NASA's Perseverance rover carried a small instrument called MOXIE specifically to test a piece of this technology, demonstrating that oxygen can indeed be extracted from the thin, carbon dioxide-rich Martian atmosphere using a real working device on the actual Martian surface. I consider this a genuinely important proof of concept, and I don't want to understate its significance. But I also want to be honest about the gap between what MOXIE actually demonstrated and what a real mission would require. MOXIE produced oxygen at a rate of a few grams per hour, an experimental proof of concept operating many orders of magnitude below the scale of tons of propellant an actual crewed return vehicle would need. Scaling this specific chemical process up to the required industrial capacity while ensuring the equipment survives Mars's extreme temperature swings. Its abrasive, electrostatically charged dust that has historically degraded solar panels and mechanical systems on multiple previous robotic missions, and years of continuous, unattended operation represents an engineering challenge, substantially different in kind, not simply in scale, from what MOXIE has actually proven. I want to walk through a second structural difficulty that flows directly from this same underlying problem: the complete absence of any possibility of rescue or resupply once a crew commits to the mission, and how this specific feature of Mars missions differs from every previous exploration endeavor in human history, including ones people sometimes compare it to. Historical exploration expeditions, even extraordinarily remote and dangerous ones, generally retained at least some theoretical possibility of rescue, however difficult or slow that rescue might actually be to arrange. Antarctic expeditions, even in the earliest and most dangerous era of polar exploration, existed on the same planet as any potential rescue mission, connected by an ocean that, however treacherous, ships could eventually cross. A Mars mission crew, once their return trajectory window has closed behind them and the next window won't open for many months, exists in a situation genuinely unprecedented in human exploration history. Even if Earth understood exactly what was going wrong and exactly how to fix it, there would be no physical way to deliver help, parts, or rescue capability to Mars on any time scale that could meaningfully save a crew from certain categories of failure. This absence of any rescue option changes the entire engineering philosophy required for every system aboard the mission in a way I think doesn't get emphasized enough in public discussion. Engineers designing a Mars mission's life support, propulsion, and habitat systems cannot rely on the kind of iterative, real-world troubleshooting that has resolved countless problems during previous spaceflight programs, where an issue identified during a mission could be diagnosed by ground control, with a fix designed, tested, and sometimes even physically delivered to the crew, all while the mission continued. Every system aboard a Mars mission has to be engineered to a standard of reliability and equipped with sufficient onboard spare parts, tools, and redundancy to handle failure modes that mission planners can only predict in advance, based on analysis and testing conducted entirely on Earth, without the benefit of the real-world operational experience that has always, throughout the history of spaceflight, revealed problems nobody fully anticipated beforehand. I want to connect this to a third structural difficulty, one I've touched on before but want to frame differently here. The sheer duration over which every mission-critical system has to function without failure, and why this duration specifically threatens a return journey more severely than the outbound journey. A Mars mission's total duration, using efficient trajectories, runs to roughly 2.5 to 3 years, driven by the orbital mechanics requiring a wait of 15 to 18 months on the Martian surface before a favorable return trajectory window opens again. This means that by the time a crew actually begins their return journey, every system they depend on for that journey, the return vehicle's propulsion system, its life support, its structural integrity, will have already been sitting on or near the Martian surface for well over a year, exposed to Mars's harsh environment before the crew ever climbs aboard and asks it to function flawlessly for another 6 to 9 months of transit back to Earth. This creates a specific asymmetry in risk between the outbound and return journeys that I think deserves direct attention. The outbound spacecraft launches from Earth, freshly checked, tested, and verified immediately before departure, using infrastructure and expertise available in essentially unlimited quantity. The return vehicle, by contrast, has to have survived over a year of exposure to Martian dust storms, extreme temperature cycling between day and night, and the general wear of extended, unattended operation. Before the crew can even verify, in any meaningful sense, that it remains capable of performing the function their survival depends on entirely. Mission architectures generally propose extensive remote monitoring and diagnostic capability for the return vehicle during this waiting period, allowing mission planners on Earth and eventually the crew themselves once they arrive to check on the vehicle's condition. But remote monitoring can only reveal problems the diagnostic systems were specifically designed to detect, and cannot substitute for the kind of thorough, hands-on inspection and repair capability available for spacecraft prepared immediately before departure from Earth. I want to address directly why I think this combination of factors, dependence on autonomously manufactured propellant, the complete absence of rescue capability, and the extended, unattended waiting period the return vehicle has to survive before use, represents something genuinely different in kind from previous spaceflight challenges, rather than simply a more extreme version of problems space agencies have already solved. Every previous human spaceflight achievement, including the Apollo program's moon landings, which I recognize represent the closest historical comparison people often reach for, benefited from what I'd call continuous engineering presence. The ability to test, verify, and if necessary, modify or replace critical hardware right up until the moment it was actually needed. With a functioning chain of expertise and manufacturing capability remaining accessible throughout the mission's planning and execution. A Mars return mission breaks this continuous chain in a way no previous mission has, requiring mission planners to commit a crew's survival to a piece of infrastructure that has to complete its most critical function successfully generating tons of usable rocket propellant, entirely on its own, on another planet, based on nothing more than remote monitoring and a track record established months or years earlier with the actual moment of truth. Whether the manufactured propellant is genuinely sufficient in quantity and purity to safely power the return vehicle, arriving only once a crew has already traveled all the way to Mars and has no practical alternative but to trust the system that awaits them. I think this is the honest core of why Mars return missions are so much harder than the outbound journey alone might suggest, and why so many individually well-understood engineering problems, propellant production chemistry, radiation shielding, life support reliability, physiological effects of extended reduced gravity, combine into something that mission planners have spent decades studying without yet declaring themselves fully ready to attempt with actual human lives. It's not that any single piece of physics forbids the mission. It's that the mission requires breaking for the first time in human spaceflight history the continuous chain of engineering verification and rescue capability that every previous crewed mission, however dangerous, has still managed to preserve in some form. I find myself thinking about this structural problem in relation to something I understood deeply during my own years directing Los Alamos, a comparison I've drawn before but want to sharpen here specifically. Even the most consequential and technically demanding project I ever oversaw benefited from something a Mars return mission cannot have: the ability to test our central hypothesis at full scale before committing to using the result in an actual, irreversible operation. The Trinity test, whatever else can be said about its consequences, existed precisely because we understood the value of verifying, under real conditions, that our design actually worked before deploying it in a situation with no possibility of correction. A Mars return mission's propellant production system cannot be tested this way, at full scale under actual Martian conditions, before a crew's survival depends on it, because the only way to fully verify it works at the scale required is to actually run it remotely on Mars for the better part of a year, with no astronaut present to intervene if something goes wrong during that critical verification period. I want to close by being honest about where this leaves the broader question of Mars mission feasibility, because I don't think the structural difficulty I've described here represents an impossible barrier in the way faster than light travel genuinely is impossible. It represents instead an unprecedented requirement for demonstrated reliability in autonomous remote infrastructure at a level beyond what any previous human spaceflight program has ever needed to achieve, because no previous program has ever needed to place a piece of equipment on another planet, run it without human supervision for the better part of a year, and then trust human lives entirely to what that equipment produces. Every individual piece of this problem, the specific chemistry of extracting oxygen and producing methane from the Martian atmosphere, the engineering required to make that equipment durable enough to survive Martian conditions unattended, the monitoring systems needed to verify its progress remotely, is, as far as current chemistry and engineering understanding suggests, solvable. What separates a Mars return mission from actually happening isn't a missing piece of fundamental science. It's the considerable remaining distance between demonstrating this technology at the small scale MOXIE has already proven, and demonstrating it reliably, autonomously, at the full industrial scale an actual crewed mission would need to trust with human lives, a gap that mission planners continue working to close, carefully and deliberately, precisely because the structural nature of this specific problem leaves no room for the kind of real-time correction and rescue that has made every previous human spaceflight achievement however dangerous, ultimately survivable when something unexpected went wrong.